So in section 3, we're going to talk about differentiability. So let's now, okay, so like the last one, talk about like segue, right? Number 37, the derivative doesn't exist. So let's now finally talk about what are the different ways that the derivative might fail to exist. Okay, one is if there is a discontinuity. Okay, so if there is a discontinuity where in this case look at this one, there's a jump discontinuity, right? That means at that point the derivative will not exist, right? Because if you go to the left and right, it's sort of not a continuous point that you're looking for the derivative. Okay, so one is a discontinuity. Next, if there is a corner, like we saw with the absolute value, and the official name for that is a corner, okay? So here we would say, for example, okay, so here f prime of x is not differentiable at x equals 0 because it's not continuous, okay? You will see that every single theorem in calculus starts with if a function is continuous, then, okay? Here, f prime at 0 from the negative side is not equal to f prime at 0 from the positive side, so it's not differentiable. Another one is a cusp, okay? A cusp is different from a corner, right? In that at the cusp, you have two branches that are sort of going into one another, okay? It's not a corner at all. So if you look at this situation here, so look at the slope here, okay? It's like, I don't know, negative, 2 or whatever, right? Or negative 1. Here, it's still negative, but a little bit steeper. Negative, but a little bit steeper. So, like the slope is going from like negative 2 to negative 4 to negative 5 and so on. And then as you go further and further here, the slope is getting a higher and higher like absolute value. So for example, like negative 10, right? The steeper it goes, the higher that number goes, right? And then finally here, you might have like a slope that's like almost infinitely large, like, negative infinity or something. It's like a vertical line, okay? And then same thing on this side. Look, if you look at the slope here, it might be like a slope of 1. Here it's a little bit steeper, so it's like a slope of 2. A little bit steeper, like slope of 3, maybe a slope of 10, and 12, 20. And then if you go down here, the slope is a positive number, but very large, okay? So here, the slope is almost like positive infinity, okay? And here, the slope is like negative infinity. They don't have the same slope here, and so here, the differentiability fails to exist. Okay? So it's not differentiable. So the graphs touch, the slopes don't. Because on the one hand, you have a negative slope. On the other hand, you have a positive slope. Okay?
Abrupt change. But
it's not an abrupt change. Okay, here it is. When you have a cusp, this is all you need to know. When you have a cusp, in here there is almost like a vertical line on both ends, but one is positive, one is negative slope, so it fails to exist, okay? All you need to know about this is that if it's a cusp, it's not differentiable, and you also need to know where does a cusp happen. A cusp happens when you've got something like this. Where you have, for example, x to the power of a fraction and the denominator is odd, okay? So f of x is equal to x to the power of even over odd, okay?
Not odd over odd?
Not, correct. Okay, next, so that's all you need to know. Don't think too much about the theoretical, what's happening to the slopes, okay? Okay, then you have a vertical tangent. A vertical tangent is when here it actually like becomes vertical for a point before it, levels out again. That happens when you have a cube root. So when you have an odd root, okay?
Any odd root or just
Yeah, an odd root, like a cube root, fifth root, whatever, an odd root. Okay, so that's all you need to know.
okay.
Okay? Okay. Take a look here for a minute now.
The vertical tangent is also non-differentiable?
Huh?
It's not differentiable.
Correct. All four of those are not differentiable. Okay, so let's look at the left and right hand limits here and find where f is not differentiable. So if you look here, you have y equals x squared. And we know that with y equals x squared, basically, like the function is differentiable everywhere. Here we have 1 over x. And then here, there seems to be a point, okay? When you have two different functions connected to each other, that's another example of a corner, okay? So now let's prove mathematically whether or not it has a derivative. So this is happening at x equals 1, right? So let's see what happens, what's f prime of 1 from the negative side. From the negative side, my function is x squared. So I'm going to say, okay, limit as h approaches 0, 1 plus h squared minus f of 1, 1 squared over h, right? F of a plus h squared minus f of a. So this is the limit as h approaches 0, 1 plus 2h plus h squared minus 1 over h. Okay, so here, let's factor out an h. We get 2 plus h over h. These go away, and the limit is 2. So the slope there is 2. Okay, in grading your tests, take a look here. At each step, I have an equal to, okay? When I grade your tests, I often see this. Okay, there is an equal sign there, and then that's it. This is not math. This is just symbols. There is no progression here, right? They're just symbols. So we need to put equal signs between every single step. Don't make me start taking points off for this, okay? All right, so now let's do it from the positive side. F prime at 1 from the positive side. This is the limit as h approaches 0. Okay, now, f of a plus h, 1 over 1 plus h, minus 1 over 1 over h. Okay, here, we're going to multiply the top by 1 plus h times 1, okay? And then here, 1 plus h.
But why are you using a different formula?
I'm not using a different formula.
She just skipped the right.
This is y on this side.
Oh, y.
This is
one
y
of
on
that.
the other side. Okay, so when I distribute here, I'm going to get 1 minus 1 plus h. So another thing, this is a parenthesis here. Most of the mistakes on these things were because people didn't put parentheses here and they missed a negative there. Over h times 1 plus h. So what happens here? Limit h approaches 0, 1 minus 1 minus h. You have no idea how many people missed that minus h. They left it as a plus. And then, things just don't work out that way. Okay, so this goes away. Limit as h approaches 0, negative 1 over 1 plus h. When we plug in 0, we get negative 1. Okay, so look at what happened. The slopes are different from both sides. Okay, we could have seen that visually, but that's not math, right? Seeing it isn't enough. You have to show it mathematically. So we say f prime at 1 from the negative side is not the same as f prime at 1 from the positive side. Therefore, it's not differentiable at x equals 1. And you will be asked, why? What type of, different non-differentiability? And you say it's a corner. A cusp will only happen when you have x to the power of odd or even. When you have two different functions connected to each other, that creates a corner. Cool?
Cool.
Yeah.
Wait, not fully.
Whenever you have two different functions connected to each other, one function, another function connect, and the slopes are different, that's going to be a corner.
But what about,
A cusp is only when you have x to the power of, as I just said that. Okay, all right. Okay, these things somehow never come out.
I just want to see how you're writing it.
We did it in the first part.
What are those three dots? Therefore.
Yeah.
For where you multiply by 10 plus h and 1,
For some reason, these graphs never come out right when I switch to PDF. I don't know why, and I thought I fixed it this time, but it's fine. You guys have them in like bigger form on your papers. So differentiability implies local linearity. What does that mean? In calculus, most of the time, we just look at one point of a graph, not the life of it, like not the entire life of it. So what is a differentiable function, right? What does it look like? Well, it's locally linear. That means if a function is differentiable at a point, if you zoom in there, the more you zoom in, the more it'll straighten out at that point and look like a line. So for example, like if you look at this one, this is y equals negative x minus 3, blah, 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 right? And if we look at x equals 3, that's this point here, okay? As you see over there. Now, if we zoom in over there, you see how it looks like it's a little bit more linear. It looks more like a line, right? Yeah. This is the point. And then if you zoom in even further, you can see on your paper that it's totally a line. So if a graph is differentiable at a point, then it's going to be, when you zoom in, it's going to look linear, like a line. Hey guys, let's focus up here, please. Okay, like over here, when you zoom in, it's not going to look like a line, no matter what you do. Okay? So this is what we're talking about. Okay, so...
The differentiable is when they're not equal.
Huh?
Differentiable is when they're not equal.
No.
That's how we find it.
Differentiable is when the derivative from the left and the right is the same. Okay, go ahead and take out your calculators, please. Okay. Okay. In the menu here, I'm sorry, not in the menu, in the graphing part here, I want you to type in x squared and just graph x squared. Okay. Now, listen. Okay. So I'll give you about 10 seconds to do that. Yeah.
Wait, we're just graphing x squared?
Yeah.
It's okay. You won't need it. Just, you can still do this. Okay? Okay, now, raise your hand if you have not graphed yet. Okay. Graph x squared. That should be very quick. Now, press menu. Analyze graph. Most of what you're going to be doing is analyze graph. Look at number 5. It says dy dx. That's derivative.
No way.
Now where? Okay, before you do anything, it says position. We're going to find dy dx at x equals 2. So just without doing anything, press 2, enter, and there we go. You see here at x equals 2, it finds the derivative, it's 4. Okay? Yeah. Yes. Right. Okay. Now, go to the home screen. Go to the home screen. You can press the calculator button under escape or whatever. Go to the home screen. We're going to do the first part here, okay? Because this is a different way to do it. Press menu. Number 4 is calculus, because that's what we're doing. Okay, press escape, press this button, menu, in the home screen. Okay, guys, look up here. Look, everybody up here for a minute. Hey, guys. So menu, calculus. Number 1 is numerical derivative. Now, this is the variable x, fine. Press tab, go to, and then you're gonna find it at x equals 2. So put 2 here. Press enter. It gives you this template. Do you see here? Okay? Do you see that vertical line there? This is what I was showing you guys last time. Evaluated at x equals 2. Now, what is the function? X squared. Type in x squared and just press enter and it gives you a 4. Okay.
So did all that work?
All that work. Okay.
You know what's crazy? One of us knew this on the test.
Okay. So
That's why we have that hand.
let's put a star next to this. Okay? Because this is one of the most important theorems that we're going to come across. Differentiability implies continuity. That means if a function is differentiable at a certain point, then by default, it's continuous at that point. Okay? That's it. If a function has a derivative at x equals a, then it's continuous at x equals a. However, it doesn't go in the opposite direction. We cannot say if a function is continuous, then it has a derivative at a certain point. Because look here, is this continuous? Yes, the absolute value is continuous. But is it differentiable at x equals 0? It's not. So the converse is not true. But if it's differentiable, then it's continuous at that point. Okay? Converse is not true. Okay? Okay, so next one. Okay, next one. Take a look here. You have a graph over a closed interval D. At what domain points does the function appear to be differentiable, continuous, whatever? Well, I'm not going to read the other part. Let's just divide and conquer. A. At what part does it appear to be differentiable? So take a look. This function starts at -2. We know that here it's not going to be differentiable, right? Because there is a corner. Okay? So here's what we're going to do. Over here is a corner, so not differentiable. Where else do you think it's not going to be differentiable?
0.
At x equals 0, it's not going to be differentiable. And where else? Itai, where else? You are right, at 2 as well.
Wait, why is it not differentiable at 0?
Why is it not differentiable at 0? Because it's a discontinuity. Okay, that's on page 1 of this lesson. Okay, so, okay, we'll get back to it.
Is it continuous?
At -2 to 1, at -2 to -1, sorry. Okay. At -2 to -1, it's differentiable. It's not differentiable at -1, so I have to have an open parenthesis there. And then, it's differentiable from -1 to 0, but I can't include -1 or 0 because it's not differentiable there. It's differentiable from 0 to 2, and then again from 2 to 3. Okay, next, okay, B. Where is it continuous but not differentiable? So we already highlighted the points where it was not differentiable. Where is it continuous but not differentiable? So of the places where it was not differentiable, the only place that it's continuous is here at the corner. Okay? So at x equals -1, it's continuous, but not differentiable. And then, where is it neither continuous nor differentiable? That's at x equals 0 and x equals 2. So, to recap, we said at x equals -1, it's not differentiable because it's a corner. At x equals 0, there is a jump discontinuity. At x equals 2, there is a removable discontinuity. Okay. Let me move past a little bit and then I'll come back, okay? All right. So, look at this one. You are told the function fails to be differentiable at x equals 0. You already know that it's not differentiable at x equals 0. We just have to figure out why. Okay. In this case, a little bit. In this case, it's what is it? It's a cusp. Because you have x to the power of even over odd.
Cusp.
Okay? So you just say it's a cusp. That's it. Okay? Okay. In this case, at x equals 0, there is a vertical tangent. There is a infinite discontinuity, right? So there is an infinite discontinuity. Okay? None of these. A vertical tangent was when you had an odd root. Okay, thank you for raising your hand. Yes.
So if it's a discount.
All values for which the function is differentiable, right? Okay, when we talk about find all values, we are really talking about an interval, okay, where the function is differentiable. So, okay, so how is it not differentiable? You always have to know it has to be a cusp, a corner, a vertical tangent, or a discontinuity, right? And you have to know by now, like a absolute value has a corner. This is a rational function, and we're seeing the pattern. Rational functions have vertical asymptotes, so that's what we have to look at, okay? There is definitely a discontinuity. So it's easier to first locate the points where it's not differentiable, okay? I always start with, is there a discontinuity? And with rational functions, there is always a discontinuity, okay? So let's factor this. Okay. So we know that there is a discontinuity at x equals -1 and x equals 1. Nowhere else is there a discontinuity. This is not a cusp function. This is not a vertical tangent function, right? So these are the points where the differentiability does not exist. So we say it's differentiable on -infinity to -1, -1 to 1, 1 to infinity. This is it. Okay. The next one, you have an odd root, okay? So when you have an odd root, you look at the stuff inside the root, okay? When this is equal to 0, okay, it's not differentiable. Okay, so the point where that filling is equal to 0. So here, we take that filling, the x minus 2, set it equal to 0. X equals 2 is where there is a vertical tangent. Okay? How did we know that? Because we've memorized that when you have an odd root, it means vertical tangent. How do we find the vertical tangent? We go inside the root, set it equal to 0, that's where it is. So it's continuous from -infinity to 2 and 2 to infinity. Okay, Sarah, remember IVT, intermediate value theorem. This is the intermediate value theorem for derivatives. And here's what this says. if A and B are 2 points on an interval on which f is differentiable, then f prime, which is the slope, takes on every value between the slope at A and the slope at B. So let's see what that means. Suppose this is a point A, and I don't know, this is a point B. Okay? Here we go, and B is here. Okay? Look at what the slope is here, right? Suppose it's like, I don't know, +3 or something, right? And then as you go up here, right, the slope is ever changing. And suppose it changes to like 0 or something, right? If this is a differentiable function, it means it's differentiable everywhere from A to B. It means it has a slope everywhere from A to B. And that slope does not change abruptly. Then in going from here to here, and as the slope is changing from one value to another value, it's going to take on every single value. So for example, as the slope changes from like -4 to 0, it's going to hit every single value until it reaches 0. Like it's not going to skip a value. Okay? That's the intermediate value theorem for derivatives. Okay? All right. So this is section